Now that we know that we can always project down onto a closed subspace of a Hilbert space, we're going to show two corollaries of that fact that will be very helpful in the coming lectures. So let's have H a Hilbert space, and let's have E a subspace of that Hilbert space, which is not the whole space. And we're going to prove two things. So the first thing is that we're going to prove that you can always find a U in H, but not in E, that has norm 1 and such that the distance between U and E is exactly 1, right? So you can always find vectors on the unit sphere that are far enough away from any subspace that is not the whole space. And the second thing we're going to prove is that H splits into the orthogonal sum of E and E perp, where E perp is the set of all those vectors H that are orthogonal to anything in E. Okay, so I want to prove these two important facts. So let's do one first. How do I construct that U? Well, I just pick any V that is in H but not in E, and I define U to be V minus its projection onto E, and then normalize that, so divide by the norm. So I know that I'm not dividing by 0 because V cannot be equal to its projection if it's not in E, and I want to show that this U does the job. So obviously it has norm 1. I've normalized it exactly to do that. And if I look at the distance between U and E, well, it is the length of the vector U minus its projection onto E. And then I'm going to use the fact that PE is a linear map and replace U by its value. So I can factor out the 1 divided by norm of lengths of V minus PEV, and then this is multiplied by V minus PEV minus PE of V minus PEV. And this is using linearity, but then using linearity again, I get 1 divided by this quantity times V minus PEV minus PEV plus PE of PEV. Okay, but PE of PEV, well, PEV is already in E, so PE of PEV is just PE of V. So I get minus 2 PEV plus 1 PEV, that's 1 PEV, and so this is just 1. Okay, that proves 1. So this is sometimes called Ries's lemma. This is very simple in this context. You can always find a point on the unit sphere at a distance 1 of any non-trivial closed subspace. I should have precised that this is closed here. We needed that in the proof of the existence of the projection, of course, because we used a Cauchy sequence argument and took a limit, and we needed to know that the limit was in E, and closedness is critical for that. Okay, let's prove 2. So I want to prove that H splits as E plus E perp. So I'm going to have to show that there always exists a decomposition of any vector in H as an element of E plus an element of E perp. And to have uniqueness of that decomposition, I need to show that the intersection of E and E perp is trivial. It's only the 0 vector. And that's easy to show because E intersected E perp is the set of all H in E that are also in E perp. So they're also such that HV is 0 for all V in E. But in particular, you can take V to be H, and so this is included in the set of all those H which have norm 0, and that is just a 0 vector. So the intersection is trivial, and that guarantees, that's a little exercise you should do, uniqueness of any decomposition of a vector in H into a vector in E and a vector in E perp. But now let's show that this decomposition exists. So to do that, given H in H, I can write H as its projection onto E plus itself minus its projection. Right, and this is obviously in E, and so what we need to show is that H minus PE of H belongs to E perp. Right, so it's orthogonal to any vector in E. Now to do that, let's give ourselves a epsilon of room. So let's have an epsilon. We're going to send it to 0 eventually, but that's going to be helpful in proving what we want to prove. And let's give ourselves a generic vector V in H. So I'm going to compute H minus PEH, the norm of that, minus, well, really a generic element in E that I'm going to write as epsilon V minus epsilon PE of H. Right, so let's expand that. So when I expand that, I get the norm of H minus PEH, an epsilon square times the norm of V minus PEH, and then I get minus 2 times the inner product of H minus PEH with V minus PEH. Okay, and what can I say about this? Well, this is part of the characterization of the projection, that this quantity has to be less or equal to 0. So I have a negative sign in front. This means that this entire thing has to be greater than norm of H minus PEH squared plus epsilon squared V minus PEH squared. Okay, that's fine. So to do this, let's take a V in E and let's give ourselves an epsilon worth of room. It's going to allow for a perturbation argument and sending epsilon to 0. So I'm going to expand H minus PEH plus a little something, or minus epsilon times V minus PE of H. Right, so let's perturb a little bit the ideal realization of the distance between H and E. Expand that, we get H minus PEH squared plus epsilon squared V minus PEH, and the cross term is minus 2 epsilon, inner product H minus PEH with V minus PEH. Now, interestingly enough, I can say that H minus PEH squared is smaller than this quantity, and that is just because this here is a vector in E, right? Because E is a subspace. So because this quantity here realizes the distance between H and E, this has to be a greater quantity. Okay, but now in this inequality I can simplify on both sides this quantity, and I get that 0 is less or equal to epsilon squared V minus PEH squared minus 2 epsilon H minus PEH, inner product with V minus PEH, and then I can reorganize this inequality and simplify and divide by epsilon on both sides, and that gives me that the inner product of H minus PEH with V minus PEH is smaller than epsilon over 2 times this norm V minus PEH squared, and now I can send epsilon to 0. So this tells me that H minus PEH inner product with V minus PEH is less or equal to 0 for every V in E, but then I can choose the element of E that is of the form of some generic element omega plus PEH. So this tells me that H minus PEH W is less or equal than 0 for every W in E. Okay, but if I do that, because E is a subspace, I also get that H minus PEH inner product with minus W is negative for every W in E. And so if you combine the two things, let's actually combine them straight away here, then what do I get? I get that the inner product of H minus PEH with a generic element W has to be 0, because it has to be both less or equal than 0 and greater or equal than 0. And that is exactly saying that H minus PH is in E Perp, concluding the proof. Okay, we now come to the conclusion of this second chapter and prove our key minimization result in Hilbert spaces, and that's a theorem due to Stampacchia in 1963. It's very similar to the Lax-Milgram theorem. It's a generalization of it, where instead of working on the whole space, we're going to be working on a closed non-empty convex subset. Obviously, convexity, as we've seen, play a key role, as it often does in optimization question. So we have a coercive continuous bilinear form, exactly like in the Lax-Milgram theorem, and we're going to show a very similar conclusion that whenever you have a linear form, you can find a unique solution in your convex set K to this optimization problem. This is now an inequality over the convex subset, as opposed to being an equality as we did have in the Lax-Milgram theorem. So let me just show you the Lax-Milgram theorem again. So continuous coercive bilinear form, no convex set, we're just working on the whole space, and we're finding in H a unique solution to an equality like that, the bilinear form being equal to the action of a linear functional. And here it's not an equality, it's an inequality of the relationship between this bilinear form and this linear functional. So I'll show you in a second that this is a little more general. And just like the second part of the Lax-Milgram theorem, in the special case where A is symmetric, we get a very neat variational characterization as this solution U to our problem being the minimizer of a certain quadratic function. Now, let me just show you that this is indeed a generalization of the Lax-Milgram theorem. So let's make a remark here. If K is H, what do we get? So we get that A U V minus U is greater than phi V minus U, and we get that for every V in H, and we have our U in H, right? So there exists a unique U in H. So this implies that AUW is greater than phi of W for every W in H, right? And because every W can be written as V minus U, in the form V minus U, for V equal W plus U, obviously. And not only this is true, but because this is true for every vector omega, of every vector W, sorry, we also can multiply this vector by any real number, and the inequality will stay true. So this is similar to what we've seen in the proof of the corollary a minute ago. Once you have inequalities like that over an entire subspace, and you can multiply by -1, then you also get the inequality in the other direction. So you get that AU omega is greater than phi omega. I keep switching between omega and W because I've written them the same way, it seems. So I get that, and I get the same thing with a minus sign. And then by linearity of phi and by linearity of A, I can multiply all of that by -1 and get the opposite inequality, and therefore that gives me that a uw is equal to phi omega for every omega in H. So this means here that Stampacchia's theorem really implies Lax-Milgram theorem. Okay, so we're going to prove this theorem of Stampacchia, and this going to imply the Lax-Milgram theorem. And let me remind you one more time that once we have Lax-Milgram theorem, we also get this neat corollary here that the PDE minus Laplacian u plus lambda u equal f as a weak solution for every f in L2 of omega. Put in a different way, there is an inverse to the linear map minus Laplacian plus lambda times the identity. That's a direct consequence of all of these theorems. So we've brought this question, this is really a variational approach to PDE. We've brought down this PDE question to a question that is linear algebraic / variational in nature, and then we've reframed that in an even more general context of minimization in Hilbert spaces, and we're going to prove this much more general theorem about convex optimization in Hilbert spaces that's going to have this very neat chain of implications. So let's have a look at the proof now. So what do we need to do? We need to find a u in K such that a of u v minus u is greater than phi of v minus u for every v in K. Okay, so let's try to turn this question that involves a bilinear form A and a linear functional phi into a question about inner product. Now that's what the race representation theorem is going to help with. So by race representation theorem, what have we got? So we have that for every v, so well, we have that there exists a unique, let's call it f, in H, such that for every v in K, but even for every v in H, phi of v is the inner product of f with v. That's because phi is a linear function. That's literally what the race representation theorem gives us. It represents this linear function as an inner product. Now, on the other hand, given a u in H, whatever that u may be, we can find also a element of H, let's call it a of u, that represents the linear map v goes to a of u v, because a is bilinear. So we can find an element au in H such that a of u comma v is the inner product of a of u with v. Right, that's another application of the race representation theorem. That's for all v in H. So really our question is to find a u in K such that for every v in K, let's rewrite our inequality. We have the inner product of au with v minus u being greater than the inner product of f with v minus u, and that is equivalent to saying that for every v in K, a u minus f inner product with v minus u is non-negative. Now I could even multiply that by a positive number, it would not change anything. So this is really equivalent to saying that for every, let's call that rho, for every v, we have that rho times au minus rho times f, should write it like that, rho times f, inner product with v minus u is non-negative. So this gives us a bit more flexibility in choosing that rho. Now this here is very reminiscent of the description of the projection onto the convex set U. Indeed, I could rewrite that, adding and subtracting U, and say that for every rho and for every V, I'm asking for rho A of U minus plus U minus rho times F minus U in a product with V minus U to be positive, to be non-negative. And that would be saying that, what? That would be saying that for every rho U happens to be the projection onto K of rho of F, rho times F minus rho times AU minus U. Actually, those are no, minus that. Right, because we have this characterization in terms of this type of inequality of what the projection is. So this is really telling me that this is the projection of that, or minus times that to have a negative. Okay, so what we are looking for really is a fixed point equation here. And I have U on the left hand side and a function of U on the right hand side. So I'm going to define a map, let's call it S subscript rho, from H to K, that takes an element U to the projection onto K of minus rho times F plus rho times A of U plus U. And what we want is that we want a fixed point from that map. So we need to show that there exists a unique U in K such that S rho of U is U. And because S rho of U is in K, I mean, if I have a fixed point, it's going to be a fixed point in H actually. It's automatically going to be in K because it's going to be the projection onto K of something. So if I have this fixed point of the map S rho, then I satisfy this family of inequalities, which is exactly saying that I have this family of inequalities that I want in my theorem. So we've translated this question about finding an element U that solves a set of inequality to a question about finding an element U that is a fixed point of the map S rho. And what's great about it is that we have this parameter rho that we can choose. And you know from the Banach fixed point theorem, we're going to try to show that S of rho is a strict contraction. And then, well, because we're in a Hilbert space, this will guarantee that that it has a fixed point. Right, so I've reduced the problem to showing that I can pick a rho that to my liking, that guarantees that S of rho is a strict contraction. Let's try to do that now. So to show that S rho is a strict contraction, I'm first gonna prove that PK, the projection onto a convex set, is always Lipschitz continuous. So that's my claim here, is that PK of U minus PK of V, the norm of that is always going to be smaller than the norm of UV for any U, V in H. So how do we see that? This Lipschitz continuity of the projection onto a convex subset, we just remember that U minus PKU in a product with V minus PKU has to be less or equal than 0 for every V in K, and in the same way V minus PKV in a product with U minus PKV has to be positive for every v in k. I should not call that v, of course. That's for every w in k, that's for every w in k here. And then I'm going to pick my w so that I get on the first line u minus pku pkv, which is definitely an element of k, minus pku is less or equal than 0, and v minus pkv pku minus pkv is less or equal than 0. Now let's put that in the right order. U minus pku inner product with pkv minus pku is less or equal than 0. I'm trying to get this quantity here, which is what I want to control in my claim. And here let's multiply both by minus 1, and I get pkv minus v, and here I get pkv minus pku. Now I can add the two things, and adding them gives pkv minus pku plus u minus v inner product with pkv minus pku has to be smaller or equal than 0, and this is saying that the norm squared of pkv minus pku has to be smaller than v minus u inner product with pkv minus pku. And then you can use Cauchy-Schwarz and obtain that pkv minus pku, the norm of that squared, is smaller than the norm of v minus u times the norms of pkv minus pku. And now you divide by this quantity on both sides, unless it's 0, but if it's 0, the claim is trivial anyway. So this proves our claims that pk is Lipschitz continuous. And let's have another look at the definition of S rho. I'm claiming that this is going to help show that S rho is a strict contraction for an appropriate choice of rho. Now, indeed, so let me remind you that S rho of u is, by definition, pk of minus rho times f. Is that what it is? Yes, minus rho times f plus rho times a of u minus u. And so when I look at S rho of u minus S rho of v for any u and v in H, what do I get? Well, by the Lipschitz continuity of pk that we've just proven, we get that this is smaller than rho of a u minus rho of a v plus v minus u. Norm of that squared. Now I'm going to use the linearity of the map. U goes to a of u, and which is a consequence of it's defined from the race representation theorem. And I'm going to expand this norm. So that's going to give me rho square of a of u minus v, norm of that squared, plus norm of v minus u, and then the cross product, which is plus 2 rho inner product of a of u minus v with v minus u. Okay, and now it's a good time to remember what that is in terms of the bilinear form. So I have rho squared of a of u minus v squared plus v minus u squared minus 2 rho of a of u minus v u minus v. So to finish, the last thing we have to show is the variational characterization when a is symmetric. And really the idea here is that if I have a bilinear form that is symmetric, continuous, and coercive, it really is just another inner product. So let's see that. So we have that for all u and v in H, delta norm of u squared is smaller than a of u, and that's smaller than c times u squared. Right, that's by continuity and coercivity. So A of UU is a quantity that is equivalent up to some constant, fixed constant, to the norm of U squared. So I'm going to define, well, this was really just for all U in H, but now for all U and V in H, I want to define the inner product of U and V adapted to A as being A of UV. Now this is bilinear, and the quadratic form associated with that is equivalent to the norm of the Hilbert space that I started with. So exercise, you can check that that H with this inner product, this new inner product, is a Hilbert space, and so its norm, where's its norm, that I'm going to denote by norm adapted to A, which is the inner product of whatever it is by itself, if you square it, equivalent to the original norm. Right, so I have a new Hilbert space with a new, some more deformed inner product which has been modified by A. So my inner product between U and V is now A of UV here. So nevertheless, I have a Hilbert space with respect to this new inner product, so I have race representation theorem. And this representation theorem tells me that for every E phi in the dual of H, there exists a unique G in H such that for all V in H, phi of V is given by the inner product against G, but the inner product being now the inner product adapted to A. Right? I'm using race representation theorem in the Hilbert space H with respect to this inner product. And well, by definition, this is A of G comma V. And you can see, you'll see that by doing the exercise, of course, that the fact that A is symmetric is important in proving that this is indeed a inner product. Okay, so now that I've rewritten phi of V as an A of GV, my condition, that is that for every V in K, A of U comma V minus U is greater or equal to phi of V minus U. This takes a neat form in terms of the A inner product, right? This tells me that the A inner product of U with V minus U has to be greater or equal to the A inner product of G with V minus U. And that is really saying that for every V in K, what is it? G minus U inner product with V minus U A inner product is less or equal than 0. Now, this is exactly a characterization like what we have in our very first theorem of this chapter, Theorem 2.1. That tells us that U is going to be the projection of G onto K, but in the Hilbert space that has the norm adapted to A. And what is that telling me? Well, it's telling me that G minus U minimizes the distance between a generic V in K and the point G. But that's with respect to the A norm. And, well, let's square that and rewrite that in terms of our bilinear form, in terms of what, sorry, this is the A norm too, in terms of what the A norm is. So what have we got here? We've got that A of G minus U has to be the infimum of A of V minus G, V minus G over all V in K. And then we can expand this and we get A of GG plus A of UU minus the cross term, and we use symmetry here, equal to the infimum of A of GG plus A of VV minus 2 A of VG, also using the symmetry. Now we have A of GG on both sides. This has nothing to do with what we're taking the infimum over. We can take it out of both sides and we can divide by 2. And so we get 1/2 of A of UU minus A of G, comma U equal to the infimum of A, 1/2 of A of VV minus A of VG over all V in K, which is exactly the variational characterization that we were promised. And this 1/2 that, you know, might have looked a little strange at first, in the first expression we had for the Lax-Milgram theorem, for instance, it's natural. It really is coming from the fact that we have a 2 popping up when we expand the square norms and we look at the cross terms. And that concludes the proof of Stampacchia's theorem, and therefore concludes the proof of Lax-Milgram theorem, and therefore concludes the proof of the existence of solution to PDEs of the form minus Laplacian u plus some positive number lambda u equal to f for an f in L2.